If you're here to finally understand quantum computing in a way that actually makes sense, you're in the right place. Whether you've heard about its potential to revolutionize industries, break encryption, or accelerate scientific discoveries, this video will give you a clear, easy-to-follow explanation. Quantum computers don't just process data faster, they change the way information itself is handled. With the power to perform mind-bending calculations beyond the reach of classical computers, they could transform everything from security to scientific breakthroughs. But how do they actually work? By the end of this video, you'll understand what makes quantum computers so different from traditional ones, and why they're considered the future of computing. You'll learn how they use strange quantum properties to solve problems faster than any supercomputer, and discover the challenges scientists face in making them practical. Most importantly, you'll see how quantum computing could soon impact industries, technology, and even your everyday life. Quantum computing is an advanced field of technology that applies principles of quantum mechanics to perform computations beyond the capabilities of classical computers. Unlike traditional computing, which relies on binary bits, zeros and ones, quantum computing leverages qubits, which can exist in multiple states simultaneously due to the phenomena of superposition and entanglement. This ability allows quantum computers to process massive amounts of data and solve complex problems at speeds that classical computers cannot achieve. Researchers and engineers are working to develop quantum computers that could revolutionize industries such as cryptography, artificial intelligence, drug discovery, and climate modeling. While still in its infancy, quantum computing has the potential to shape the future of computation and transform how we solve some of the world's most complex problems. The origins of quantum computing date back to the early 20th century, when physicists first developed quantum mechanics to explain subatomic behaviors. However, it was not until the 1980s that physicist Richard Feynman suggested using quantum mechanics to create more powerful computers. The idea gained traction in the 1990s when researchers like David Deutsch and Peter Shor developed theoretical models and algorithms demonstrating the potential of quantum computation. The first experimental quantum computers emerged in the early 2000s, utilizing trapped ions and superconducting circuits. Over the past 2 decades, significant advancements have been made, with companies like IBM, Google, and D-Wave developing quantum processors. The race to build practical quantum computers has accelerated, with governments and private organizations investing billions into quantum research. Today, quantum computing continues to evolve as scientists work to overcome challenges like decoherence, error correction, and scalability. Traditional computers, also known as classical computers, process information using bits, which are the fundamental units of data. A bit can have one of 2 states, either 0 or 1, and all computational operations are performed using combinations of these 2 values. Classical computers operate using logic gates, which manipulate bits to perform calculations, store information, and execute software programs. Modern classical computers rely on transistors and silicon-based chips, which have progressively become smaller and more powerful over the decades. While classical computers are extremely efficient for everyday applications such as browsing the internet, gaming, and word processing, they struggle with highly complex problems that require enormous processing power. Some examples include simulating molecular interactions, optimizing large-scale logistical operations, and breaking advanced encryption algorithms. This is where quantum computing presents a transformative advantage. Quantum computers differ from classical computers in several key ways. Instead of using traditional bits, quantum computers use qubits, which can exist in multiple states at once due to the principle of superposition. This allows quantum computers to perform many calculations simultaneously, greatly increasing computational speed for certain types of problems. Additionally, qubits can be entangled, meaning the state of one qubit is dependent on the state of another, even if they are physically separated. This entanglement enables faster information processing and more efficient problem solving. Another key difference is that quantum computers rely on quantum gates, which manipulate qubits in ways that classical logic gates cannot. While still in the experimental phase, quantum computers have the potential to revolutionize industries by solving problems that would take classical computers thousands or even millions of years to compute. However, building and maintaining quantum computers is challenging due to the fragile nature of qubits, which require extremely low temperatures and precise control to function properly. Qubits, or quantum bits, are the fundamental units of information in quantum computing. Unlike classical bits, which can only be in one state at a time, 0 or 1, qubits can exist in both states simultaneously due to superposition. This unique property enables quantum computers to perform complex calculations at speeds unattainable by classical computers. Qubits can be implemented in various physical systems, including superconducting circuits, trapped ions, and photons. However, qubits are extremely delicate and can lose their quantum properties due to external interference, a phenomenon known as decoherence. Scientists are actively working on techniques to stabilize qubits and improve quantum error correction, making quantum computers more reliable. The development of high-quality qubits is essential for achieving large-scale quantum computing and unlocking its full potential in fields such as cryptography, artificial intelligence, and materials science. Superposition is one of the most fundamental principles of quantum mechanics and is crucial to the operation of quantum computers. In classical computing, a bit can only be in one of two states, either 0 or 1. However, a qubit in superposition can exist in both 0 and 1 states simultaneously. This allows quantum computers to process multiple calculations at the same time, dramatically increasing their computational efficiency. Superposition is what gives quantum computers their extraordinary power, enabling them to solve problems like factorizing large numbers, optimizing supply chains, and simulating chemical reactions much faster than classical computers. However, superposition is highly fragile, and when a qubit is measured, it collapses into a single state, either 0 or 1. Scientists are researching ways to maintain superposition for longer periods to maximize the potential of quantum computing. Entanglement is another key phenomenon that differentiates quantum computing from classical computing. When two qubits become entangled, the state of one qubit is instantly correlated with the state of the other, regardless of the physical distance between them. This allows quantum computers to perform calculations in a highly interconnected and efficient manner. Entanglement has profound implications for quantum communication, enabling the development of ultra-secure encryption methods known as quantum key distribution, or QKD. In computing, entanglement significantly enhances processing power by enabling coordinated operations between qubits. While entanglement is a powerful tool, maintaining it over long distances and for extended periods remains a major challenge. Researchers are working on techniques to improve entanglement stability, which will be essential for building scalable and error-resistant quantum computers. Quantum measurement is a fundamental concept in quantum mechanics and quantum computing. Unlike classical computers, where bits retain their values unless modified, quantum computers operate on qubits that exist in superposition until they are measured. When a qubit is measured, its superposition collapses into one of its possible states, either 0 or 1. This collapse means that once a measurement is made, the qubit loses its previous quantum properties and behaves like a classical bit. This unique characteristic of quantum measurement makes quantum computing both powerful and challenging. Since measuring a qubit disrupts its quantum state, quantum computers must carefully manage when and how measurements occur. Researchers are developing techniques such as quantum error correction and fault-tolerant computing to mitigate measurement-related disruptions and ensure reliable computation. The ability to extract useful information from quantum systems while minimizing collapse is key to harnessing the full potential of quantum computing. Quantum computing offers several advantages over classical computing, particularly in solving complex problems that classical computers struggle with. One of the biggest advantages is computational speed. Because of superposition and entanglement, quantum computers can perform multiple calculations simultaneously, allowing them to solve certain problems exponentially faster than classical machines. For example, quantum computers have the potential to revolutionize cryptography by breaking encryption schemes that would take classical computers thousands of years to crack. Another advantage is efficiency in solving optimization problems. Quantum algorithms can find the best possible solutions for logistics, finance, and artificial intelligence applications in a fraction of the time it would take a classical computer. Additionally, quantum computing is expected to advance drug discovery by simulating molecular structures and chemical interactions with unprecedented precision, potentially leading to the development of new treatments for diseases. While quantum computing is still in its early stages, its unique capabilities make it a transformative technology with vast potential across various industries. Quantum algorithms are specialized computational procedures designed to leverage the unique properties of quantum computing. Unlike classical algorithms, which rely on step-by-step logical operations, quantum algorithms exploit superposition and entanglement to perform complex calculations more efficiently. Some of the most notable quantum algorithms include Shor's algorithm, Grover's algorithm, and the quantum approximate optimization algorithm, or QAOA. Shor's algorithm is particularly significant because it can factor large numbers exponentially faster than classical algorithms, posing a potential threat to current cryptographic systems. Grover's algorithm speeds up search operations, making it useful for tasks such as database searches and pattern recognition. Other quantum algorithms have applications in machine learning, material science, and financial modeling, enabling researchers to solve previously unsolvable problems. As quantum hardware continues to advance, more quantum algorithms are being developed to tackle real-world challenges across diverse fields. Shor's algorithm is one of the most famous and impactful quantum algorithms, developed by mathematician Peter Shor in 1994. The algorithm is designed to factor large numbers exponentially faster than any known classical algorithm. This capability is particularly significant because modern encryption systems, such as RSA encryption, rely on the difficulty of factoring large numbers as a security measure. If a sufficiently powerful quantum computer is built, it could use Shor's algorithm to break these encryption schemes, rendering many existing cybersecurity protocols obsolete. As a result, researchers are now working on developing quantum-resistant encryption methods, known as post-quantum cryptography, to ensure data security in the quantum era. While large-scale quantum computers capable of implementing Shor's algorithm do not yet exist, ongoing advancements in quantum hardware suggest that cybersecurity professionals must prepare for a future where quantum threats become a reality. Grover's algorithm, developed by Love Grover in 1996, is another fundamental quantum algorithm that enhances search capabilities. Classical search algorithms must check each entry in a database one by one, making large-scale searches time-consuming. However, Grover's algorithm leverages quantum superposition to search databases quadratically faster than classical methods. For example, if a classical computer needs to search an unsorted database of n items, it would require approximately n steps to find the target item. With Grover's algorithm, a quantum computer could find the item in roughly the square root of n steps, making searches exponentially more efficient. This improvement has wide-ranging applications, from optimizing search engines and data retrieval to enhancing machine learning models and cryptographic security. While practical implementation is still limited due to the current limitations of quantum hardware, researchers anticipate that Grover's algorithm will play a crucial role in future quantum computing applications. Quantum computing is still in the early stages of development, with most existing quantum computers being experimental and limited in their capabilities. Unlike classical computers, which have been optimized over decades, quantum computers face significant challenges in scaling up their number of qubits while maintaining stability. Currently, companies such as Google, IBM, Microsoft, and startups like Rigetti and IonQ are at the forefront of quantum computing research. They are working to develop practical quantum processors that can outperform classical supercomputers in specific tasks. IBM's quantum experience allows researchers and developers to experiment with quantum algorithms on real quantum processors, fostering innovation in the field. Google's Willow chip, announced in December 2024, is a next-generation quantum processor designed to enhance qubit stability, minimize computational errors, and improve processing efficiency. As an evolution of the Sycamore processor, which demonstrated quantum supremacy in 2019, Willow integrates advanced error correction methods to increase reliability. The Willow quantum chip demonstrates exceptional computational speed. It completed a benchmark task in under 5 minutes, a feat that would require today's most powerful supercomputers 10 septillion years. This remarkable speed is attributed to advanced quantum error correction and a focus on high-quality qubits. Willow achieves exponential error reduction, a critical factor in maintaining accuracy during complex quantum calculations. Rather than simply increasing the number of qubits, Google prioritized enhancing their quality, leading to significantly improved performance. This allows Willow to efficiently solve problems far beyond the capabilities of classical computers. However, practical applications remain limited, and researchers are still exploring ways to improve quantum hardware, minimize error rates, and increase coherence times. The field is rapidly advancing, with more funding and interest from governments, universities, and private industries worldwide. Despite its immense potential, quantum computing faces several major challenges. One of the most significant challenges is error correction. Qubits are highly sensitive to their environment and can easily lose their quantum state due to decoherence, leading to computational errors. Quantum error correction codes are being developed to mitigate these errors, but implementing them requires a large number of additional qubits, making large-scale quantum computers difficult to build. Another challenge is maintaining quantum coherence, as even minor interactions with the surrounding environment can cause qubits to lose their entangled state. Furthermore, the extreme operating conditions required for quantum computers, such as ultra-low temperatures close to absolute zero, make them expensive and complex to maintain. Scalability is also a concern, as increasing the number of qubits while ensuring they remain entangled and functional presents significant engineering difficulties. Researchers are actively working on different approaches, such as superconducting qubits, trapped ions, and topological qubits, to find the most reliable and scalable technology for future quantum computers. Decoherence is one of the biggest obstacles in quantum computing. It occurs when qubits lose their quantum properties due to interactions with their external environment. This can happen because of temperature fluctuations, electromagnetic interference, or even small vibrations. Once decoherence sets in, quantum information is lost, rendering the computation unreliable. The fragile nature of qubits means that they need to be carefully shielded from outside influences, which is why most quantum computers are kept in highly controlled environments with temperatures close to absolute zero. Scientists are actively researching ways to mitigate decoherence, including error correction techniques and materials that enhance qubit stability. One promising approach is the development of topological qubits, which store quantum information in a way that is more resistant to errors. If researchers can find ways to significantly extend coherence times, quantum computers will become much more practical for solving real-world problems. To make quantum computing more practical, scientists are working on several methods to improve qubit stability. One of the most common approaches is quantum error correction, which involves encoding information redundantly across multiple qubits so that errors can be detected and corrected without collapsing the quantum state. Another method is using better materials and qubit designs, such as superconducting circuits, which have longer coherence times. Trapped ion qubits, which use individual atoms as qubits, have shown promise due to their natural stability. Additionally, researchers are exploring topological qubits, a theoretical concept that could provide more robust quantum states with fewer errors. Another strategy is to improve cooling techniques to reduce noise and interference, allowing qubits to maintain their superposition and entanglement for longer periods. If these techniques can be successfully implemented, they will pave the way for scalable and fault-tolerant quantum computers. Quantum error correction is one of the most crucial areas of research in quantum computing. Unlike classical computers, where errors can often be corrected by redundancy checks, quantum computers require specialized techniques due to the fragile nature of qubits. A major challenge is that qubits cannot be directly copied due to the no-cloning theorem, making traditional error correction methods ineffective. Instead, scientists use quantum error correction codes such as the surface code, Shor code, and Bacon-Shor code. These techniques work by spreading quantum information across multiple qubits so that errors can be detected and corrected without directly measuring and collapsing the quantum state. However, implementing error correction requires a significant increase in the number of physical qubits, which makes large-scale quantum computing difficult. Researchers are also exploring fault-tolerant quantum computing, which involves designing quantum processors that can perform reliable computations even in the presence of errors. If fault tolerance can be achieved, It will allow quantum computers to perform complex calculations for extended periods without data loss, paving the way for practical and large-scale quantum computing applications. Governments around the world are investing heavily in quantum computing research, recognizing its potential to transform industries and provide strategic advantages. The United States has launched the National Quantum Initiative, which allocates significant funding for quantum research and development. The European Union's Quantum Flagship Programme is a €1 billion initiative aimed at advancing quantum technologies over the next decade. China has also made significant strides, investing billions into quantum research and establishing the world's first quantum satellite, MISSIUS, which successfully demonstrated quantum key distribution for secure communications. Canada, Australia, and Japan are also investing in quantum research, fostering collaborations between academia, government, and private industry. Quantum computing has the potential to revolutionize artificial intelligence and machine learning by significantly increasing computational power. Traditional machine learning algorithms rely on large data sets and require extensive processing time. Quantum algorithms such as quantum-enhanced support vector machines and quantum neural networks can speed up these computations, leading to faster and more efficient AI models. Quantum computers can also improve optimization tasks, which are essential for training deep learning models. Additionally, quantum-enhanced reinforcement learning could enable AI to make better decisions in real-time applications such as robotics, financial modeling, and healthcare diagnostics. Researchers are actively exploring how quantum computing can be integrated with AI to solve complex problems that classical computers struggle with. As quantum hardware continues to improve, AI-driven industries may see significant advancements, opening new possibilities for scientific research and real-world applications. Quantum computing could play a critical role in space exploration by enhancing mission planning, navigation, and communication systems. One of the most significant challenges in space travel is optimizing fuel consumption and spacecraft trajectories, which require highly complex calculations. Quantum computers can process these calculations much faster than classical computers, allowing for more efficient space missions. Additionally, quantum computing can help analyze vast amounts of astronomical data collected from telescopes and space probes, leading to a better understanding of cosmic phenomena such as black holes, dark matter, and planetary formations. Another promising application is the use of quantum communication for secure data transmission between Earth and space-based systems. Climate modeling and weather forecasting involve analyzing vast amounts of atmospheric data, which is computationally intensive and time-sensitive. Traditional supercomputers struggle with simulating complex climate patterns due to the limitations of classical computing power. Quantum computing offers a promising solution by providing faster and more accurate simulations of climate models. With quantum algorithms, scientists can analyze multiple variables simultaneously, leading to more precise predictions of extreme weather events such as hurricanes, droughts, and heat waves. One of the most significant implications of quantum computing is its impact on cybersecurity and encryption. Modern encryption methods such as RSA and ECC rely on the difficulty of factoring large prime numbers, a problem that classical computers take thousands of years to solve. However, Shor's algorithm, a quantum algorithm, can break these encryption methods exponentially faster, posing a major threat to current cybersecurity systems. To counteract this risk, researchers are developing post-quantum cryptography, which includes quantum-resistant encryption techniques designed to withstand quantum attacks. Quantum computing has the potential to revolutionize healthcare and drug discovery by significantly accelerating the process of molecular simulation and medical research. Traditional drug discovery relies on complex simulations and trial-and-error methods, which can take years and cost billions of dollars. Quantum computers, however, can model molecular interactions at the quantum level, allowing researchers to analyze how drugs interact with proteins and DNA more efficiently. This capability can lead to the faster identification of new medicines, personalized treatment plans, and breakthroughs in understanding diseases such as cancer, Alzheimer's, and genetic disorders. Additionally, quantum-enhanced machine learning can improve diagnostic techniques by analyzing large datasets of medical records and identifying patterns that indicate early signs of disease. As quantum hardware and algorithms advance, the healthcare industry stands to benefit from improved drug development, more accurate medical imaging, and enhanced patient care. The financial industry deals with massive datasets and highly complex calculations, making it an ideal sector for quantum computing applications. Quantum algorithms can be used for risk analysis, fraud detection, and portfolio optimization, enabling financial institutions to make faster and more accurate decisions. Quantum computing has the potential to transform energy production, storage, and distribution by optimizing complex chemical and physical processes. One of the most promising applications is in the development of new materials for batteries and superconductors. Quantum computers can simulate the behavior of atoms and molecules, leading to the discovery of more efficient energy storage solutions, such as high-capacity batteries for electric vehicles and grid storage. Quantum sensors utilize quantum mechanics principles to achieve unprecedented precision in measurement and detection. These sensors have applications in various fields, including medical imaging, geology, and navigation. In healthcare, quantum sensors can be used for highly accurate brain imaging, improving our understanding of neurological disorders. In geology and mineral exploration, quantum gravimeters can detect underground resources such as oil, gas, and rare minerals with greater accuracy than classical sensors. Quantum-enhanced gyroscopes and accelerometers can improve navigation systems, particularly in submarines and spacecraft, by providing highly accurate positioning without relying on GPS. Quantum computing and quantum mechanics have opened new frontiers in secure communication, particularly through quantum key distribution, or QKD. Traditional encryption methods such as RSA and ECC rely on the difficulty of factoring large numbers, a challenge that quantum computers could potentially overcome using Shor's algorithm. This raises concerns about cybersecurity and the need for quantum-resistant encryption. QKD enables ultra-secure communication by leveraging the principles of quantum mechanics, ensuring that any attempt to intercept data would be immediately detectable. As quantum computing continues to advance, it brings with it significant ethical and security concerns. One of the most pressing issues is the potential for quantum computers to break current encryption systems, leading to vulnerabilities in personal privacy, financial security, and government data protection. As quantum computing continues to evolve, the demand for skilled professionals in quantum mechanics, quantum programming, and quantum engineering is rapidly increasing. Universities and research institutions are expanding their quantum computing curricula, offering specialized courses and degrees to train the next generation of quantum scientists and engineers. Quantum computing is expected to play a significant role in shaping the future of emerging technologies. In combination with artificial intelligence, quantum computing could enhance deep learning capabilities, leading to breakthroughs in medical research, climate modeling, and advanced robotics. Quantum computing also has potential applications in blockchain technology, where it could improve the security and efficiency of decentralized systems. Another promising area is the integration of quantum computing with the Internet of Things, where quantum-enhanced optimization could manage vast networks of connected devices more efficiently. Additionally, the advent of quantum internet, an ultra-secure communication network based on quantum entanglement, could redefine data security and privacy. Quantum computing represents one of the most exciting frontiers in modern technology, offering the potential to solve problems beyond the reach of classical computers. While still in its early stages, rapid advancements in quantum hardware, error correction, and algorithm development are bringing us closer to practical applications. The impact of quantum computing will be felt across numerous industries, from artificial intelligence and healthcare to finance and cybersecurity. However, challenges remain, including improving qubit stability, reducing error rates, and developing quantum-resistant encryption. Continued collaboration between governments, private companies, and academic researchers will be essential in overcoming these obstacles and ensuring the responsible development of quantum technology. As we move into a new era of computing, quantum technology is poised to redefine what is possible, opening the door to discoveries and innovations that were once considered science fiction. The next decade will be critical in shaping the quantum landscape, and the world is watching as this revolutionary technology unfolds. Quantum computing is an exciting but complex topic, and we'd love to hear your thoughts. If you have any questions, drop them in the comments below, and let's explore this fascinating field together. Thank you for joining us on this journey through quantum computing. Please like and share the video, and please do not forget to subscribe for more videos.